Hello, my name is Lukas Eichmeier, and in this part of low temperature solar thermal power systems, we are going to speak about collector physics. In order to be able to calculate the efficiency of a solar collector, we need to understand the underlying physics. In this video, we are going to speak about the flat plate collector as an example in order to calculate the efficiency. We have already spoken about the flat plate collector in previous videos, and you might remember that the flat plate collector uses a glass window in order to reduce the heat losses. Within the collector, an absorptive material absorbs the impinging solar radiation and converts it to heat. Insulation material at the back side of the collector reduces heat losses, as well as the glass window at the front also reduces heat losses. A flat plate collector looks something like this. We see the solar radiation, which usually has a spectrum of about 300 to 2500 nanometers, impinges onto the flat plate collector. About 8% are directly reflected on the glass window, and about 2% of the impinging solar radiation is absorbed within the glass window. The remaining part of the impinging solar radiation passes through the glass window and is impinges onto the absorber. Parts of this impinging radiation onto the absorber is then absorbed at the absorber itself, and a small part is also reflected of the absorber. The product of the transmissivity of the glass window and the absorptivity of the absorber, tau G and alpha A, is commonly referred to as the optical performance. In these videos, whenever we have properties with an asterisk, we are speaking about properties of materials that refer to the solar spectrum, and properties without an asterisk refer to properties of the thermal spectrum. As a result of the absorbed heat in the absorber itself heats up. Within the absorber, a heat transfer fluid is circulated, which is actually heat up, and the usable heat, here shown with the green arrow, can be extracted. As a result of the absorber heating up, it also emits thermal radiation and also loses heat through free convection. On the outside of the solar collector, we also have losses due to thermal radiation and forced convection, for example, due to the wind. In order to calculate now the collector efficiency, we're going to look at a control volume of the absorber itself. The absorber here is shown as a red dot with a mass, a specific heat capacity Cp, and its temperature. We're going to draw the boundaries of our heat balance, which we're going to apply with the green dashed dotted line, which is marked as Cv for control volume. We can see in the equation at the bottom that the change of stored heat with time, dq stored over dt, equals the supplied power q sol minus the usable power q use minus the heat losses. For a steady state system, the change of stored heat within the control volume is 0. In the next few minutes and the next few slides, we're going to look at how to actually calculate the supplied power, Q sol, the usable power, Q use, and the heat losses, Q loss. The solar heat input of a solar collector can easily be determined by looking at the solar light path. We can see, as before, solar radiation impinging onto the glass window, parts of it being reflected, parts of it being absorbed, and only the part, tau G, with the transmissivity transmits through the glass window and impinges onto the absorber. Here again, the product tau g times alpha A is referred to as the optical performance. Q SAW can easily be calculated knowing this as tau g times alpha g times the global irradiation times the collector area AC. The heat losses of the solar collector can be determined using the thermal resistance model. Generally speaking, we use the equation shown to the right to calculate the heat losses. Here, UA effective is the effective UA value, which is proportional to the heat losses. We also have to take into account the mean absorber temperature, TAM, and the ambient temperature. Heat losses within the solar collector are composed of three different heat losses. We have heat losses through conduction, which are usually relatively low. We can insulate the reflector. We can insulate the solar collector quite good at the backside. We also have heat losses due to thermal radiation, which are here shown as the error between the absorber and the glass window, and by the error from the glass window to the ambient. And finally, we have heat losses due to convection, free convection on the inside, and forced convection on the outside. As I said, mainly due to wind. In order to calculate the effective UA value, we apply the thermal resistance approach. Here on this slide, you can see an example of a parallel configuration of heat conduction. The thermal resistance approach works very similar to the calculation of electrical resistances. For a parallel configuration, the UA value, the effective UA value, can be calculated simply as the sum of the individual heat resistance, UI, or also K, the heat transfer coefficient, times the effective heat transfer area, AI. For a serial configuration, the effective UA value is calculated with the equation shown here, very similar again to the calculation of the serial resistance in an electrical circuit. I would suggest, if you have troubles to calculate thermal resistances, to have a look at the heat transfer book of your choice. What we can recommend here at KTH is the fundamentals of heat transfer and of heat and mass transfer from Incropera. To calculate now the useful heat and the efficiency of the power system of the solar collector, we can just use the equation which we have shown before and calculate the usable heat, QUs, with the equation shown here. The efficiency, as in any system, can be calculated as the useful heat or the useful power divided by the power available at the solar collector. We can see in the equation here that we have the product again of tau g times alpha A, the optical performance, minus the term on the right, which corresponds to heat losses. The useful heat of the solar collector can therefore simply be calculated as the difference between the solar input and the losses of the absorber. We can calculate the useful heat now with the equation shown, where we see again the product of tau g times alpha g, which corresponds to the optical efficiency, and then on the right side we have the losses. The efficiency of the collector can easily be calculated, as in any power systems, as the ratio of the useful heat or the useful power divided by the total power available at the collector. As I said, on the left side, tau g times alpha g corresponds to the optical performance, and the term on the right side corresponds to the heat losses. In this slide, we have the temperature TAM, which is the mean absorber temperature, which is not that easy to calculate. In order to make the calculation of the efficiency simpler, we would like to replace the temperature TAM, so the mean absorber temperature, with the mean fluid temperature. In order to do so, we need to change the equation of the efficiency slightly. We introduce the collector efficiency factor F prime, which is always lower than 1. We replace the mean absorber temperature with the mean fluid temperature, which is simply calculated as the arithmetic mean between the inlet temperature to the collector and the outlet temperature to the collector. Finally, we can calculate the efficiency of the collector with the equation shown at the bottom. The collector efficiency factor F prime, as I said before, takes into account that the mean absorber temperature is higher than the mean fluid temperature. Typical values of F prime are somewhere between 0.9 and 0.95. F prime usually depends on the thickness of the absorber, the heat conductivity of the absorber material, the width of the fins, if there are any fins in the collector, the connection between the riser and the absorber, and also the heat transfer in the riser. This was low temperature solar thermal power systems, where we spoke about collector physics and collector efficiencies. In the next video, we're going to speak about the collector efficiency of different types of solar collectors.